Okay, so this is about probabilistic programming, as is the session. This particular talk is about probabilistic programming as a way of statistical modeling. So a way of describing statistical models by writing programs, and the focus is random graphs. These are three methods that we're using to do this: Markov categories, graphons, and nominal sets. You'll see a bit about it as we go through. I've got all these brilliant co-authors, of which Hongseok, Cameron, and Sean are here, and the others might be online, or you can find them elsewhere. This project that's been going on for quite a while, maybe 6 or 7 or 8 years, so that's why we've accumulated, I guess, quite a few authors. Let me show you the main theorem, and then we'll chat a bit more about random graphs. Okay, so the main theorem is this. The following data are equivalent. A well-behaved implementation, I'll say what well-behaved means, of a particular abstract type, and a graphon. Okay? Now, the abstract type is an abstract type of graphs, so it has a type of vertices, which we can implement however we like. Is there a laser? No. And then it's a generative graph, so we can generate new vertices. That's why there's this new, which gives us a new randomly a new vertex. And it's a graph, so there's an edge relation. So 2 vertices, is there an edge between them? Okay. This is in a probabilistic programming language in some sense. And on the other hand, a graphon. So graphons have been rediscovered several times over the last 50 years in probability theory, in combinatorics, in graph theory. One view on graphons, and we'll come to this a little bit, is it's a function from the unit square to the unit interval. So we can draw it as a kind of heat map. Here are 2 heat maps. There's a lovely book by Lovash about this concept. Okay, so these things are the same, that's the point. So you have like a programming view on graphons. Let me dig in a bit more about random graphs then. Okay, so high level, random graphs are interesting for all kinds of reasons, modeling all kinds of networks, social networks, a physical network for disease modeling perhaps, biological networks or graphs, molecular structures, but also lots of things can be encoded as graphs. So equivalence relations are graphs, so we can understand clustering in terms of graphs, finding which things are roughly the same. And then, as I said, it's not just a practical thing, there's also deep connections to combinatorics and graph theory. Let me show you my view to hone in a little bit. We've been developing a language or a library called Lazy People, Lazy Probabilistic Programming Language. And this was the idea was to investigate kind of stochastic processes and infinite probabilistic structures from a programming point of view using laziness. So that has all kinds of stuff in it, but one thing we can talk about is graphs. And here's an inference thing I did. You can read the code here, it's literate Haskell and it's not very complicated. Given the graph on the left, suppose we found it in the wild by measuring something, where did it come from? And we can infer, perhaps it came from a geometric situation, right, with quite a high likelihood, where you can see this is actually the same graph, but it's now mapped onto the sphere, and points that have edges between them, vertices that have edges between them, are close. Okay. So these are the kind of questions you might ask. Let's zoom in a little bit more on this interface then and talk about that to be a bit more, even more concrete. So the interface we need to implement vertex somehow. We need to say what's new and what's edge. So here's an example of an implementation, but there are lots of implementations. The point is to explore them. This is a geometric one like we just saw a second ago. And here the vertices are points on the sphere. So we could implement that as x, y, z coordinates or Euclidean coordinates or polar coordinates. It's different ways of doing it. Here's pseudocode. You can read the actual implementation online. So new randomly picks a point on the sphere. And let's do it uniformly. So we uniformly pick a point on the sphere, and that's a vertex, a new vertex. There's an edge between 2 vertices if the distance between them is less than some parameter theta. Right, if and only if the distance between them is less than some parameter theta. So we can then randomly sample. Here's a random sample with, I think, 14 vertices. And theta was picked to be pi by 6, and it's a 3D sphere. But we can vary those things. And what you saw earlier was an inference problem, and we inferred that theta is about 60 degrees for this particular graph. Okay, so that's one implementation. But probably looking at this, you can imagine other implementations of this interface that would be quite useful. For example, other shapes, not just a sphere, maybe a torus or a cube or a tetrahedron or something more wacky, right? But also, we've said that there's an edge if and only if the distance is less than theta. Maybe you want to say, like, people are more likely to be connected or know each other if they're close, and less likely if they're far apart. So make that a bit fuzzy. Okay? So let me show you a second implementation. I won't sort of show you all the implementations because there are lots. The second one example is an Erdős-Renyi graph. And here we forget about the geometry altogether. And in fact, there's no kind of correlations between the vertices. So we can, how do we understand vertices? Well, just going to give them names. So we can do that by like a uniform distribution. And is there an edge from vertex V to vertex W? Well, it's just toss a coin. So it's independent for any pair of vertices if there's an edge between them. Right? This is the Erdős-Renyi graph. It's very hard to visualize, I think, but this is a kind of a visualization of it. Okay. So that's sort of the other extreme where there's no geometry and the chances of edges are now random. Okay, so we'll come back to those two extremes towards the end of the talk, hopefully. But that gives you two examples of interfaces. Right, yes, let me show you another, like a more precise way we might use the interface. So I won't show you like the full graph inference problem, but we can ask, is there a horn? Let me show you that, okay? So what do? We draw 3 nodes, A, B, and C. We could do this in anything that implements the interface. And then ask, is there an edge from A to B and an edge from B to C, but not an edge from A to C? A horn for me is a triangle without a base. I just made it a bit more interesting than a triangle, so yeah. And this returns a Boolean. It's either true or false. We either get a horn or we don't. So it's a random Boolean now. So with some probability, we'll get a horn, and with some probability, we won't. So it's describing a random Boolean. Okay, and as I said, we could run this on the Erdős-Renyi thing here. It'll be, I think, 1/8 will be the probability of getting a horn. But we could also run it for the geometric things. It makes perfect sense, just using the interface. Okay, so I'll come back to that horn example a bit later as well. But let me first just have a chat at a higher level about the idea of interfaces in probabilistic programming. So we're focusing here on graph inference, but we could also look at regression, which is perhaps a even more famous kind of statistical problem. And there, we're also interested in a very similar abstract type, but slightly different. So now we're interested in some parameter space. Maybe it's linear regression, like in the top left, where you have the slope and the intercept as the parameters. So we've got some distribution on the slope and the intercept, and then rather than an edge relation, we have an evaluation function that, given the parameters for the function and an argument, produces a result. Perhaps some of you went to Ohad's tutorial on Monday. We've looked at these kinds of things quite a lot. For example, the quasi-Borel spaces was meant to explore these kinds of structures. Okay, so that's another kind of abstract type. It looks a little bit similar in flavor to the graph one. But there's plenty others to study, which we mentioned a bit in the paper, but I think there's still a lot of work to do. But the high-level view, I guess, is that abstract types and interfaces in probabilistic programming correspond to important statistical structures. And I guess it's a two-way street because we can start to inform statistics by programming. Right. Okay. So let's move back to the theorem and start to explore a bit what well-behaved means. Okay, so back to graphs and exploring a bit more about the theorem. Okay, so what is a well-behaved implementation? So some of our implementations need to use hidden state to describe the structure. So that's why it's a little bit subtle. Let me step away from graphs for a second, though, and talk about probabilistic programming with sort of more basic interface to try to agree with you on what kind of structures, basic structures, we should have in probabilistic programming. So here I've got normal. Don't worry if you don't know what a normal distribution is. It's just a distribution on the real numbers. Doesn't even have to be on the real numbers. But I'm drawing A and B from normal, and then I'm doing 2A plus B to return a result. Okay, and the point is I've got 3 programs here, and they're all the same. They should all do this. They should all give the same kinds of results, but they may do slightly different things along the way. So the first one draws A and then B. The second one samples B and then A. And the third one samples C and then B and then A, but doesn't use C. Okay? So if we're thinking of maybe a Monte Carlo simulation, we might actually have some state in there if it's doing something clever. So it might do actually under the hood different things for all 3 of these programs. But I hope you can agree, like intuitively, the 3 programs should give the same statistics in the end. Because if instead of normal, let's toss a coin. If I toss a coin with one hand and then a coin with the other, it doesn't matter which order I toss coins. They don't communicate. The coins don't communicate to each other. So we can reorder these things. So let's take that as a primitive, basic axiom for probabilistic programming, that at this level, program lines can be reordered. It's like a commutativity property. So, right, so this is a view of probability from a programming language perspective, but let's bring it down to a probabilistic point of view. If we think of these programs as Monte Carlo samplers, computing integrals, here K is a continuation, what happens next, then we can understand the program on the left as a double integral over A and then B, and the middle program as a double integral over B and then A. And the fact that these integrals are the same is Fubini's theorem, which says we can reorder integrals on probability distributions. It's maybe the first non-trivial theorem of probability theory. But we're going to take it not as a theorem, but as an axiom, as a synthetic description of what probability is all about. Okay. It's not just me saying this. Several other people are arguing that we should take this kind of view of, even as a mathematical view of probability. Okay, so with that in mind, we understand what's well-behaved probabilistic programming. Let me be a bit more technical for a second for anyone who wants this, and say more precisely what's going on here. We have a distributive Markov category, it's the same monoidal category with coproducts and some extra structure. Or equivalently, and what's nice is that these things are the same, an affine monoidal monad on a category with sums. And that gives us this, the monoidal thing gives us this interchange, gives us the exchange, the commutativity. And let's insist, moreover, this is, I guess, something that I haven't seen before in Markov category literature, that we know what Booleans are. We know what random Booleans are, right? They're just like coin tosses. We don't want to have unusual interpretations of basic finite probability. So I want to have strange interpretations of the type of vertices or of real numbers and stuff like that. But for Booleans and for finite types, I don't want to do anything controversial. So to fix that, we say what we call a Bernoulli-based Markov category, which says that the numerals, the finite types, just give us stochastic matrices. Okay, so that's our formal model of what a well-behaved probabilistic programming language is. Okay, so with that, we're ready to prove the theorem. Okay, and I'll prove it by example. Don't worry. So let's start from this interface, and we've already seen the chance of a horn. This program here that draws A, B, and C, and then asks, is there an edge from A to B and B to C, but not from A to C. I'm going to do some manipulations to this program now, based on the equational reasoning that we've all agreed is okay for probabilistic programming. So let me copy the program. That's exactly the same program. They're definitely equal. And then let's use the data flow property to just flip the second and third lines. Okay? I said I can always do that. There's no variable dependency, so I can always do that. Okay, so these programs are equal, and that's our assumption. It's a well-behaved implementation. Then let me do alpha conversion. Hopefully everybody's happy that alpha conversion should be allowed. So I rename B and C. I swapped the names B and C. It may look like lines 2 and 3 reordered again, but no, I just swapped the names B and C. And now if I read this, it's talking about the chance of a horn where there's an edge from A to C and an edge from B to C, but no edge from A to B. So these two programs must be equal because I only used things that we all agreed were okay to do. Therefore, the probabilities of getting these two horns are equal, and we could also show that the third horn is equiprobable. In other words, this commutativity condition for probabilistic programming has given us exchangeability on this particular finite random graph. Okay? So the finite random graph that we're getting here is invariant under permuting the vertices. And this invariance is called commutativity. Okay. So this is an example of one particular property on a 3-vertex graph, but it works for any property of any finite graph. And this is the route then to programming. So to proving the theorem. So yeah, so to go from a well-behaved implementation that satisfies commutativity and just data flow, we get back a graphon by remembering that it's well known, or it's known in the graphon community, that a graphon is the same thing as an infinite sequence of finite random graphs that's exchangeable, that's what we just saw, but also satisfies two other conditions, consistency and locality. I won't show you those conditions, they're in the paper, of course, and they're also very simple to show using just program manipulations and basic equational reasoning. Okay? So from a program, we get a graphon by getting this infinite sequence of finite random graphs, and it's exchangeable, it's also consistent and local, therefore it corresponds to a graphon. To go the other way is a bit more non-trivial. For black and white graph, so if we think of a graphon as a heat map, if it's black and white, we have a simple implementation, and we saw the geometric implementation. A very similar one works for any black and white graphon. If it's grayscale, we need to use some hidden states, and that's where things become more interesting and complicated. So for constant gray, so ideally we'd like to build a distributed Markov category, right, that is Bernoulli based. So to do that for the constant gray one, we used Rado nominal sets, which various people have considered before, but not in this probabilistic context. And for arbitrary grayscale, we don't have a concrete method for building a Markov category, but we have an abstract one that uses some techniques from category theory. So I guess we're trying to build up a way of building these synthetic models of probability. So that's the theorem. I guess a high-level view is that abstract types in probabilistic programming connect to concepts in probability and statistics. And hopefully that's a two-way street where we learn things about programming and we learn things about statistics. Thanks.
Yeah. Do we have any questions?
Thank you, excellent talk.
Thanks.
So one question about the Boolean. So there are some applications like in computational chemistry and the combinatorial chemistry where you want to have more than graphs, hypergraphs.
Yeah.
Could you imagine an extension of what you're doing in that direction?
Absolutely, yes. So we focused here on graphons just to keep it simple. It's complicated enough, but I don't know how easy it is. There's all kinds of other structures, not just hypergraphs. Here we are, hierarchical graphs. Absolutely, these are the kinds of structures that should be studied, yeah.
Can the next speaker come forward to the podium? Any other questions?
So when you did this new operation, it was generating, in the example that you had, the edges were being generated as you did this. And obviously, if I was if the likelihood of an edge was inversely proportional to the number of nodes that was there, and which would appear in many applications of generating graphs, you wouldn't get this interchangeability property. Can you speak a little bit about just like what prevents me from? What are the conditions that are guaranteeing the interchangeability there?
Then you would need some hidden state to do this. And I guess if your hidden state gave you something that wasn't exchangeable, wasn't commutative, it wouldn't correspond to a graphon. So those are certainly interesting random graphs, but they don't correspond exactly to this familiar characterization of a graphon.
So a graphon always has these properties?
Always has these properties, exactly. Yeah.
Thank you.
Yeah.
I think we have time for one more question.
Could you explain more about the usage of the assumption about the coproduct? Is that for interpreting if the control flow or what?
Yeah, so I need a coproduct in my category. Well, I need Booleans, which I think has 1 plus 1, which is a coproduct. Okay, maybe we don't need all coproducts, but it just felt easier to say we'll have all the coproducts. Yeah. So it's an if then else interpretation, yeah.
Okay, let's thank Sam again.